So what does standard deviation really do for us? We understand we have a measure of central tendency, like means. You've been using means for most of your academic life, and so you all have this intuitive gut feeling for what a mean tells you, right? It's the average. Well, you're going to need to develop that same intrinsic sort of understanding of what standard deviation is as well. So we have a couple of additional items in this section to help try to give some understanding for what the standard deviation's really telling us. So we have the first of two rules. The first rule is called the empirical rule. And then we have a second rule that we'll see in a minute called Chebyshev's inequality. So the empirical rule is here. If a distribution of data is roughly bell-shaped, so approximately a bell-shaped distribution, then approximately 68% of the data will lie within one standard deviation of the mean. Now, what does that mean? Suppose I have a set of data, and suppose the mean of that set of data is 50, and suppose the standard deviation of that set of data is 4. Well, if I take 50 minus 4, that equals 46. I would say the value 46 is one standard deviation below the mean. If I take 50 and add 4, that would be 54. The value 54 is one standard deviation above the mean. So according to this empirical rule, if I have a bell-shaped distribution, approximately 68% of the data would be within one standard deviation of the mean. So again, if this is a bell-shaped distribution, and if the mean's 50 and the standard deviation's 4, then about 68% of the data would be between the values of 46 and 54. So that's giving me an idea of how spread out the data are. If you take a look at this visual right here, we have this bell-shaped distribution. So the mean's right here in the center. If I take the mean plus one standard deviation, I would get this value right here. If I take the mean minus the standard deviation, I would get this value right here. And 68% approximately of the data would be between this value and this value. That's what the empirical rule is telling us. Moreover, approximately 95% of the data will lie within two standard deviations of the mean. So for example, if I were to take 50, instead of just subtracting 4, if I would subtract 4 twice, so if I subtract 2 times 4, well, 2 times 4 is 8, and 50 minus 8 is 42. And the same way, if I take 50 plus 2 times 4, well, 2 times 4 is 8, and 50 plus 8 would be 58. So 42 would be 2 standard deviations below the mean. 58 would be 2 standard deviations above the mean. So according to the empirical rule, about 95% of the data values would be between 42 and 58. So again, if I look at my picture here, the mean's in the center. Here would be the mean plus 2 standard deviations. Here would be the mean minus 2 standard deviations. And again, about 95% of the data would be between this value and this value. And moreover, if I go for a third standard deviation, approximately 99.7% of the data will lie within 3 standard deviations of the mean. So if I were to take 50 minus 3 times the standard deviation of 4, well, 3 times 4 is 12, and 50 minus 12 would be 38. And if I were to take 50 plus 3 standard deviations, so plus 3 times 4. 3 times 4 is 12, plus 50 would be 62. So about 99.7% of the data would be between the values of 38 and 62. Nearly all of the data would be within 3 standard deviations if it's a bell-shaped distribution. So again, if here's the mean, if the standard deviation sigma, here would be mu minus 3 standard deviations. This would be mu plus 3 standard deviations. So between this value and this value would be about 99.7% of the data. Virtually all of the data will be within 3 standard deviations if we have a bell-shaped distribution. Now, bell-shaped distributions are also symmetric, so I can also determine other information. So for example, about half of the data would be larger than the mean, and about half of the data would be smaller than the mean. So if 68% of the data values are between here and here, then half of the 68%, about 34%, would be between the mean and this value, and the other 34% would be between the mean and this value. So about 34% of the data would be here, and about 34% of the data would be here. In the same way, I can determine that about 13.5% of the data would be between this value and this value. And 13.5% of the data would be between this value and this value. And where that comes from is 95% of the data are between this value and this value. 68% of the data is between these two values. If I take 95 minus 68, that is 27. So 27% of the data would occur here, and half of it would occur in each place. So half of 27 is 13.5. So about 13.5% of the data would be here, and about 13.5% of the data would be here. In the same way, about 2.35% of the data would be between 2 and 3 standard deviations from the mean on each side. And only, again, like if between here and here, if that's 99.7% of the data, then that only leaves 0.3% of the data to be farther away from the mean than that. And half of that 0.3% would be 0.15% here and 0.15% here. So we can really get the idea of where the data is located by value if we have a bell-shaped distribution. Incidentally, this notation that's used here is for population data, but this also works for sample. So if this was a sample, then this would be X bar, this would be X bar plus S, X bar plus 2S, X bar plus 3S, X bar minus S, X bar minus 2S, X bar minus 3S. All of that would work the exact same. The percentages would be the same is what I'm getting at. Quick example, using the empirical rule. So the distribution of the length of bolts has a bell shape with a mean of 4 inches and a standard deviation of 0.007 inches. About 68% of bolts manufactured will be between what lengths? What percentage of bolts will be between 3.986 inches and 4.014 inches? If the company discards any bolts less than 3.986 inches or greater than 4.014 inches, what percentage of bolts manufactured will be discarded? And D, what percentage of bolts manufactured will be between 4.007 inches and 4.021 inches? So there's a lot of information that's told here. First of all, we're told that the mean length of the bolt is 4 inches. So that is mu. Mu equals 4 inches. We're told that the standard deviation for these bolts is 0.007 inches. So as this manufacturer is making these bolts, there's a little bit of variation, right? And so that variation is judged by this standard deviation. It's giving us this idea of how much variation there is. We're also told that the distribution of the lengths of bolts is bell-shaped. So bell-shaped means it has tall bars in the middle and so on. So using this information along with the empirical rule, can we determine about 68% of bolts manufactured will be between what lengths? Well, we can do this with a visual. So I have this bell-shaped distribution. The mean is 4 inches, so 4 inches is going to be right there in the center, okay? The standard deviation is 0.007. So if I take 4 plus 0.007, that would be 4.007. That is 1 standard deviation above the mean. If I take 4 minus 0.007, 4 minus 0.007 would be 3.993. So 3.993 would be right here. That's 1 standard deviation below the mean. So between that value and that value, about 68% of the bolts manufactured are going to be between these two lengths. So that's going to answer my question here. 68% of bolts manufactured will be between the lengths of 3.993 inches and 4.007 inches. That comes directly from the empirical rule. Because we have a bell-shaped distribution, 68% of the data approximately will be within 1 standard deviation. So if I add the standard deviation and subtract the standard deviation from the mean, that gives me the range where the middle 68% of these bolts will be located. Question B, what percentage of bolts will lie between 3.986 and 4.014 inches? Well, if I take 4.007 and add the standard deviation 0.007 on again, in other words, if I take 4 plus 2 times 0.007, that will be 4.014. So 4.014 is 2 standard deviations above the mean. If I take the 3.993 and subtract 0.007 again, that gives me the 3.986. In other words, if I take 4 minus 2 times 0.007, that's going to equal 3.986. So in other words, these values are 2 standard deviations from the mean. So from here to here is going to be approximately 95% of the data. Approximately 95% of the bolts produced are going to be between the lengths of 3.986 inches and 4.014 inches. So the answer to the question, about 95%. I really should say about. C, if the company discards any bolts that are less than 3.986 inches or greater than 4.014 inches, what percentage of bolts manufactured will be discarded? So in other words, we already have this drawn here. 3.986 is right here. That's 2 standard deviations below the mean. 4.014, that's 2 standard deviations above the mean. Any bolt that occurs over here that's shorter than 3.896 gets thrown out. Any bolt that's over here longer than 4.014 gets thrown out. So anything over here or over here is waste. What percentage of the bolts have to be thrown out? Well, if 95% of the bolts are between here and here, then the other 5% is out here or out here. So it would be the other 5% of the bolts that would have to be discarded. So again, we know about 95% of the bolts will be useful, and that means that about 5% of the bolts will have to be discarded. So the last question, what percentage of bolts manufactured will be between 4.007 inches and 4.021 inches? I'm going to draw a new picture. So again, 4 is here. 4.007 is here. That was 1 standard deviation above the mean. 4.021 would be over here. So we want to know what percentage of the bolts are between here and here. Okay. We know that 4.007 is 1 standard deviation above the mean. We also learned over here that 4.014 was 2 standard deviations above the mean. And so if I add 0.007 on one more time, that would be 4.021. This value is 3 standard deviations above the mean. So if I pull back in my previous figure that had this stuff calculated, I know that between 1 standard deviation and 2 standard deviations above the mean, about 13.5% of the bolts will be in that range. So in other words, between 4.007 and 4.014, right there is going to be about 13.5% of the bolts are going to be between this length and this length. Then between the 2 standard deviation and the 3 standard deviation mark, so right here, that is about another 2.35% of the bolts are going to be from 4.014 to 4.021. So if I just add those together, 13.5 plus 2.35, that's going to be 15.85%. So the answer to the question, about 15.85% of the bolts produced will be between the length of 4.007 inches and 4.021 inches long. So the empirical rule only works when we have a distribution that's bell-shaped. So what if the distribution's not bell-shaped? Well, then comes in Chebyshev's inequality. Chebyshev's inequality says that for any data set or distribution, so in other words, even if it's not a bell-shaped distribution, at least 1 minus 1 over k squared times 100% of observations lie within k standard deviations of the mean, where k is a number greater than 1. That is, at least 1 minus 1 over k squared times 100% of the data lies between the values of mu minus k times sigma and mu plus k times sigma for k greater than 1. Again, this is using population notation. It also works for sample. So we could say x bar minus k times s, x bar plus k times s. So what's it really saying? So if k equals 2, k equals 2 is talking about 2 standard deviations from the mean. So Chebyshev's inequality would say take 1 minus 1 over 2 squared times 100%. Well, 2 squared would be 4. So I have 1 minus 1/4, which is 3/4. And 3/4 times 100 is 75%. Chebyshev's inequality says that at least 75% of the data are within 2 standard deviations of the mean. Now, the nice thing about Chebyshev's inequality is that Chebyshev's inequality applies to any distribution. It doesn't have to be bell-shaped. So even if I have some really skewed right distribution such as this, at least 75% of the data is going to be within 2 standard deviations of the mean. Could be more than 75%, but it will not be less than 75%. So in reality, if I compare Chebyshev's inequality to like the empirical rule said that about 95% of the data will be within 2 standard deviations if it's a bell-shaped distribution. So Chebyshev's inequality is saying it's at least 75%, even if we have a distribution that's nowhere close to being bell-shaped. So really what we know is that somewhere between 75% and 95% of the data will be within 2 standard deviations of the mean. How much depends on how bell-shaped the distribution is. If k equals 3, then Chebyshev's inequality would say 1 minus 1 over 3 squared times 100% of the data is within 3 standard deviations of the mean. So 3 squared is 9. So I have 1 minus 1/9, which is 8/9. And 8/9 times 100 is approximately 88.9%. So Chebyshev's inequality would say that at least 88.9% of data are within 3 standard deviations of the mean. So again, if it's a bell-shaped distribution, the empirical rule would tell us that about 99.7% of the data is within 3 standard deviations. Chebyshev's inequality says even if it's not even close to being a bell-shaped, it's at least going to be 88.9% of the data that's within 3 standard deviations. So that tells us between the two, somewhere between 88.9 and 99.7% of the data is going to be within 3 standard deviations of the mean. How much depends on how close to bell-shaped. The closer to bell-shaped, the closer the percentage would be to 99.7. The lower the shape is from being bell-shaped, in other words, being really not bell-shaped, the closer we would be to 88.9% of the data instead of 99.7, and so on. So I have one quick example with this. According to the US Census Bureau, the mean of the commute time to work for residents of Boston, Massachusetts is 27.3 minutes. Assume the standard deviation of the commute time is 8.1 minutes to answer the following. So we're told that the mean is 27.3 minutes, and we're told that the standard deviation is 8.1 minutes. The difference between this problem and the previous problem is we're not told about the shape of the distribution. So we have no reason to believe that this distribution is bell-shaped because the problem never told us there's a bell-shaped distribution. Since it's not bell-shaped, or at least we don't know that it's bell-shaped, we can't use the empirical rule. Instead, the best we can do is use Chebyshev's inequality. So question A, what minimum percentage of commuters in Boston has a commute time within 2 standard deviations of the mean? B, what minimum percentage of commuters in Boston has a commute time within 1.5 standard deviations of the mean? What are the commute times within 1.5 standard deviations of the mean? And then C, what is the minimum percentage of commuters who have commute times between 3 minutes and 51.6 minutes? Okay? So it's the same kind of problem that we did up here, except we have to use Chebyshev's inequality instead of the empirical rule. So question A, the minimum percentage within 2 standard deviations, that in other words is telling us k equals 2. So the answer to that is simply going to be 1 minus 1 over 2 squared times 100%. And we actually did that calculation right there. That would be 75%. So at least 75% of the commuters in Boston has a commute time within 2 standard deviations of the mean. And so 2 standard deviations of the mean in this case would be 27.3 minus 2 times 8.1. So that would be 11.1, and 27.3 plus 2 times 8.1, that would be 43.5. So 75% at least of commuters in Boston have commute times between 11.1 and 43.5 minutes. That's what this is saying. What minimum percentage of commuters in Boston has a commute time within 1.5 standard deviations? Well, that means K is equal to 1.5, 1.5. So I can do 1 minus 1 over 1.5 squared times 100. So if I pull this back in, I'm going to do 1 minus 1 divided by 1.5 squared, close parenthesis, times 100. That is equal to 55.6 approximately. So this would be about 55.6%. So at minimum, 55.6% of commuters in Boston have commute times within 1.5 standard deviations of the mean. Now, what would those commute times actually be? Well, if I take the mean, 27.3, minus 1.5 times the standard deviation, 8.1, 27.3 minus 1.5 times 8.1, that would be 15.15 minutes. And if I do the same thing, 27.3 plus 1.5 times 8.1, 27.3 plus 1.5 times 8.1, that is 39.45 minutes. So again, about 55.6% of Boston commuters have commute times between 15.15 minutes and 39.45 minutes. That's the idea. Part C, what is the minimum percentage of commuters who have commute times between 3 minutes and 51.6 minutes? Well, the tricky part of this question is we have to figure out how many standard deviations 3 minutes and 51.6 minutes are from the mean. So if I were to take my mean, 27.3, and if I were to subtract 3 times 8.1, that's 3 times the standard deviation. Well, 27.3 minus 3 times 8.1 equals 3. So this time right here, 3 minutes, is 3 standard deviations below the mean. In the same way, if I take 27.3 plus 3 times 8.1, 27.3 plus 3 times 8.1, that is 51.6. So this time right here, 51.6 is 3 standard deviations above the mean. So in order to find the percentage, knowing that this is 3 standard deviations below the mean, this is 3 standard deviations above the mean, my answer is going to be 1 minus 1 over 3 squared times 100, which we actually calculated up here already. That would be 88.9% approximately. So at least 88.9% of Boston's commuters have commute times between 3 minutes and 51.6 minutes. Again, if I knew more about the shape of the distribution, if I knew the shape of the distribution was bell-shaped, then I would be able to say maybe that's closer to 99.7%. But the fact that I don't know this is bell-shaped means the best I can say is that it's at least 88.9%.